Okay, so having finished linear and quadratic programming problems, now we take up the major task of studying the 4 families of methods that we elaborated long back, which are the standard classes of methods by which we solve constraint optimization problems. And these 4 standard families of methods or classes of methods have been actually classified so based on the dimension of the space in which the search is made. The first one is penalty methods, in which the search space is the same as the space of the primal variables, okay, R n, as if the problem is unconstrained optimization problem, and the constraints are handled by using a penalty term. We will see how it works. The second family of methods operate only on the feasible space. That means, if n dimensional design space is there and m active constraints are there, then the feasible space is n minus m dimensional and only feasible points are considered. That is a primal method. The dual method takes a completely different perspective. It says that in constraint optimization problems, the major amount of information is actually held by the Lagrange multipliers, and therefore, our first attempt should be to get hold of the correct values of the Lagrange multipliers, and therefore, we will make the search in the space of the Lagrange multipliers. That is why m dimensional space, if m active constraints are there or m constraints are there. The fourth set of methods, which is in a way the 0th set of methods, is Lagrange methods, in which we try to make the search in the entire space of x lambda mu. That is, all the unknowns that we really want at the end of the day, all of them we together search. Okay? And that is in a way the original method, because KKT conditions give you m plus n equations in m plus n unknowns. These are the unknowns that we really look for. In Lagrange methods, we try to get hold of all the unknowns together. So, first we study penalty methods, and here in penalty methods are actually the simplest methods, and therefore, in that also I will start with a particular method which one of my students in IIT Kanpur developed, which is even simpler in the sense that that does not use any of the derivatives, and it actually uses a simplex method, okay? A constrained optimization algorithm based on the simplex search method. So, and with this method he actually solved many complicated problems. Now, first the basic simplex method that you already know, that we have studied long back. Now, how do we handle the constraints? That is the question here. That is, in the framework of simplex search method, nailed and made method, how do we handle the constraints? So, a simplex, if the simplex is in the completely infeasible region, then there is one way to handle. If it is completely in the feasible region, another way to handle, and if it is across the boundary of feasibility, then there is one way of handling. All of them are quite natural, quite obvious looking. Okay? And one more issue this method settles is a problem which many of you have not faced, so do not recognize, is that when you have a problem which is a constraint problem, now many methods require you to evaluate the function outside the domain and do a few things with it along with the constraint violation values, constraint function values, and then realize that it is infeasible point, and therefore, you have to do some special things and so on. But then there may be a situation in which you may not be able to even evaluate the objective function outside the domain. For example, suppose the objective function f involves something sin inverse x 2 plus 3 x 3 square and whatever. Now, the domain of this will be bounded by the boundaries which say x 2 plus 3 x 3 square is within plus minus 1. Beyond that, you cannot even evaluate the objective function, and this was another issue which we wanted to handle, and this reorganization of simplex method handles it beautifully. How we take care of this? See, first situation, if a simplex lies completely in the infeasible region, that is, it is not in the domain, none of the vertices of the simplex is in the domain. So, there you do not even evaluate the function value, you do not even try to evaluate the function value, just evaluate the constraint function values and evaluate the constraint violations, and that is this. Okay. So, the largest one you get from here, and that is the value of the auxiliary function capital F. Small f is the objective function, and you use the auxiliary function capital F, in which we really work. Okay. And that gets defined by the constraint violation, that is sum of the violations of constraints 1, 2, 3, 4, 5, 6. Okay. So, for all the constraints at that vertex of the simplex at that point, evaluate the constraint violation and sum them up. If some constraint violation is 0, that fellow will not contribute to the sum, which is fine, and that is it. You do not evaluate the function at all. On the other hand, if the simplex is entirely in the feasible region, then that is fine. So, there is no constraint violation. So, just evaluate the objective function. If it is feasible, then you will need the objective function value, and then you evaluate. And the third case, where the simplex is partly in the feasible region, partly infeasible, that is, some of its vertices are in, some of the vertices are out. Then those vertices which are in, there you evaluate the function value. Now, suppose your space is 7 dimensional. So, there are 8 vertices in the simplex. Okay. So, suppose for 5 of them it is feasible, 5 of the vertices are feasible. So, for those 5 the function values are calculated like this. Now, the other 3 vertices are not feasible. So, out of these 5 which you found feasible, whatever is the largest function value, you call that f max, and at the other 3 vertices do not evaluate the objective function, evaluate only constraint violation, and with that constraint violation you add this f max. As a result, what will happen? All these 3 among themselves will have a gradation, this is better, that is worse, and so on, and all of these 3 will turn out to be certainly worse compared to any of these 5. So, certainly the 5 feasible vertices will turn out to be better, that is have less value of capital F corresponding to these 3 which are infeasible. Among these 3 there will be some high low, among these 5 there will be some high low, and among these 3 you can compare, all are violating constraints, among these 5 you can compare, because all of them are satisfying constraints. Okay. So, and as blocks, as en masse, these 5 will be certainly better than these 3. So, in the simplex method, when you say better than this and worse than this and worst and best, so in that all these things will settle perfectly all right in the framework. So, this is how you handle inequality constraints, right. But how do you handle equality constraints? There also you can talk of constraint violations, but then there is a problem. because constraint violation is both sides. Okay. Only on the boundary you have to have the point. Now, that is a little troublesome, because this formulation will not work, max of 0 g. Okay. So, on both sides there is constraint violation. So, equality constraints. What do we do in the case of equality constraint H? We use two terms. Okay. One is this max of the mod of H minus delta, and the other is a simple penalty term. Okay. That is a penalty parameter r times h square, h k square. Okay. So, what these two terms are doing? Suppose this is the surface on which your feasible points lie. Now, this delta element, what this is doing? It is telling that we will allow this h to be away from 0 by this much amount. Okay. So, delta is a little measure of this gap on this side as well as on this side. So, that means this much area we will allow the feasible point to be in, because for operating with the Nelder-Mead simplex method you need a volume. Okay. Without the volume you cannot do all this flipping of vertices and jumping from here to there and moving the simplex from here to there and there to there and so on. Okay. So, that is why you allow this. So, that means this delta, the larger the delta, more space you will be allowing. Okay. So, this you do, but this alone will be something awkward, because that means that the moment a vertex of the simplex is inside this, it will be considered fine, and then this, all these 5 points will be considered equally fine. Okay. And that is not what you want. You want the simplex eventually to become thin and converge on this, right. So, that alone, this channel alone will not serve that purpose. So, for that you include this quadratic penalty term, okay. A constant penalty parameter times this sigma h k square. Okay. So, on this cross section it will actually define a parabolic function like this. So, that means here it is no penalty, higher penalty, higher penalty, higher penalty, higher penalty and so on. Now, this alone also would not work, because if this with this alone, if you try to work, then it will not bring the thing in very easily, and a constraint violation may start fouling with the function values. So, but both of them together work fine, okay. And the two numbers that are key numbers here is, one is the penalty parameter value r, and the other is the channel half width delta. Okay. So, these two have to be judiciously selected. Once these two are judiciously selected, then the rest of it can be handled as we have discussed. And now, beyond this, I have linked this paper here. You can see how well it works. There are lots and lots of examples, and it has been shown that this method operates pretty fine, and much larger multi objective optimization problems also have been handled by this method. Okay. So, this is one of the simplest possible methods of constraint optimization, but the mainstream penalty methods operate in other ways, okay, which are more traditionally established. So, rather than minimizing f of x, you minimize a function of x and c, where c is the penalty parameter, and you say that the objective function is f x and you rig the function by using a penalty term, okay, in which c is the penalty parameter and p of x is a penalty function. Now, there are typically two kinds of penalty functions, that is exterior penalty functions and interior penalty functions. Exterior penalty functions have these properties. The penalty function is continuous, it has to be, and it is a positive definite function, p x is greater than or equal to 0, and p x is equal to 0 only if and only if x is feasible. That is, a feasible point is not penalized and an infeasible point is penalized by a positive amount. Okay. So, take an example, say if the constraints are this, x can be from a to b, okay, then this is one penalty function, half sigma g I x square. This angle bracket means the maximum of 0 and the value. Okay. So, if it is 0, then 0 is taken, if it is negative, then 0 is taken, and if it is positive, then its value is taken. Okay. That is this angle bracket means max 0 y. Okay. So, here since it is feasible point, it will be all 0. On this side, the penalty function, this one will be like a parabolic segment depending upon what is the c. Okay. So, with very small c, this will be the one, with higher c, this will be the one steeper, with still higher c, this, still higher c, this. Okay. So, for convergence, you will need to increase c indefinitely, and by the time c becomes very large, this becomes convergent, this converges, and that means the constraints are really satisfied. Okay. That is, in spite of such a large c, this penalty term is not shifting the point, that means this point is feasible, almost feasible. So, from outside if you come, then as you increase c, you will be, this bowl will be made stiffer and stiffer, steeper and steeper, and you will converge here. From this side, you will converge here. Okay. So, here it is like this parabola, half side of this parabola, on this side it will be half side, this half side of this parabola, here it will be flat. Okay. That is how you will get this plot. Okay. So, this is basically the plot of this. Okay. So, this is one example of such an exterior penalty function. Okay. This is a variation of that, including equality constraints also. Okay. Here the max has to be there for inequality constraints. For equality constraints, it is not needed, because both sides are violated. The same thing can be used with a positive definite weight function in between. Okay. So, that will mean half sigma w j h j square and so on. It is also possible to use an absolute penalty function like this. Okay. So, that is also possible. However, this has the problem that you will not be able to use any method using derivatives with this, because this is not differentiable. Okay. There are some interior penalty methods also, which use interior penalty function, and for using an interior penalty function or interior point method, you have to start from an internal point and then the iterates always remain inside, because the penalty basically operates like a barrier. Okay. So, this space where it is vertical boundary gets skewed like this. So, anywhere you start, you stay inside only, you can never cross this boundary, okay, of this large penalty. Okay. So, a typical form of this is, a typical example of a barrier function is this kind of a thing. Okay. So, wherever g turns out to be 0, this turns out to be infinite. Okay. And here also you will see that if g turns out to be 0, this will be minus infinity, and the ln of minus infinity is 0. Okay. So, this ln, so this is 0. So, this minus infinity, this is the barrier that works. Okay. And as you go on changing c equal to 1, not so stiff. Okay. But you see here at feasible points also there is some value of the violation, okay, that is barrier higher. Okay. So, some penalty in the feasible point also. So, what happens here is that as you increase c, see it is 1 by c here. So, as you increase c, this goes on dipping below and you approach the correct profile slowly. Okay. So, barrier methods are rarely used and used in very specialized methods, those which are called interior point methods. The kind which we saw in linear programming problem in the interior point method, there you start in the interior and very close to the convergence also you stay in the interior. Okay. So, that is how it works. Now, you say fine. So, we choose a suitable penalty function and then we construct the rigged function like this, and then we minimize this q function q, and that is the end of it, no need to study more. However, there are some issues with the penalty methods, and those issues we need to handle. There are two segments of this handling. One is what are the issues that may arise and how to handle them. There are several ways to handle them, and even after handling all of them, you will notice that penalty methods will be typically inefficient. Okay. So, what are the issues that arise? Say this is what you are trying to do, and suppose you are using a gradient based method for solving this so called unconstrained optimization problem, in which in the unconstrained objective function you have included this penalty term, through which you are thinking of handling the constraints. Okay. So, when you try to differentiate it, you get this, okay. And if you see finally, p will be dependent on the h's and g's. So, the gradient of p you can find out by taking the gradients, the derivatives with respect to h's and g's, and multiplying with them the corresponding grads. Okay. So, like this. Now, what really happens? What is the issue? What is the issue here? If you take the penalty parameter as small, then this may not make much of a dent, much of a difference. For example, if the penalty for wrong side driving is 2 rupees, then everybody will drive wrong side. Okay. So, the penalty will have no effect if the penalty parameter is small. On the other hand, if penalty parameter is suddenly large, then what happens? They say wrong side driving is death penalty, okay, or 7 lakhs fine. So, that means nobody will come to the road, because of some reason if you have to go to the right side for 1 minute and you are caught at that point, then suddenly it is death penalty or 7 lakhs fine. I mean, you can't handle it, right. So, it, and some people are caught, some people are not caught in actual human situation. Okay. So, it will be a real problem. And what is right side? A little on the right or all the way in the right. So, this will make a lot of difference. So, the problem becomes skew. Okay. So, if the penalty parameter c is large. So, while using penalty methods, if penalty method is the only thing that you are using to handle constraints, then typically the way it is advised is to solve the problem through many iterations. In the first iteration, keep penalty parameter c equal to 1, and that way you will get somewhere, which is perhaps typically very close to the unconstrained minimum, and constraints are violated by lots. Okay. And since C was only 1, very small, it was not bothered. Now, after you have converged, then make the penalty parameter 10 and run it once more from this new point, and then you will come closer to the constraint satisfaction. Not very well, okay? Still a little far away. It has started showing some kind of effect. Then in the next round you make C equal to 100 and so on. Like this, by the time you go to C equal to 10 lakh, 1 crore, you will be converging within the domain, because then a little violation will cause a large penalty. Okay. Now, if in one shot you have tried to do that, then the problem, the objective function will become so skew that original objective function will have no say in it. You will end up trying to minimize this. Okay. And this is not a rich enough function, because this will not have representation of all the dimensions involved. Okay. So, that is the issue, we will see how. So, before that, notice that when you take the gradient of this penalized function q with respect to x, then you get this, okay, and compare it with the KKT condition. Okay. In the KKT condition, what did you get? Here you see, since you are trying to minimize this as an unconstrained function, so you will be setting this equal to 0, grad q equal to 0. Okay. That means this equal to 0. In the case of KKT conditions of a proper constraint function, you get grad f plus sigma lambda I grad h I plus sigma mu j grad g j. Okay. So, in coefficients of grad g j, you typically get mu j. Here in the penalty method, as coefficient of grad g j, you get del p by del g j, and therefore, del p by del g j is taken as the penalty method's estimate of the Lagrange multiplier. Here also, del p by del h I is taken as the estimate for lambda I. That means, in every iteration, penalty method would try to give you not only a better point, better means better from the point of view of objective function as well as constraints. At the same time, if you monitor the del p by del h I and del p by del g j, you will also be able to estimate the Lagrange multipliers. Okay. This is an important piece of information, which we will be using somewhere later in some other family of methods. So, anyway, so the Lagrange multiplier estimates you get from here del p by del h I into the outside penalty parameter sitting. Similarly, here del p by del g j into the outside penalty parameter sitting. Okay. So, these are the Lagrange multiplier estimates that you get. Okay. Another observation to be made from this is that its Hessian will be extremely ill conditioned. Okay. You can see that. See, for example, take the penalty function as this. Okay. Active inequality constraints included in this. Inactive ones anyway, inactive inequality constraints will not have any say in the penalty function. So, that is fine. So, this is basically half H transpose H. Okay. And now, when you try to take the gradient of this, you get this sigma, the derivative of this is simply H into grad H. Okay. So, in other ways, this sigma notation you can replace by saying this grad H, all the vectors together assembled in a matrix, that matrix into this H vector. Okay. So, you see this is H 1 times grad H 1 plus H 2 times grad H 2. Okay. So, here what is happening? Grad H 1 is the first column, H 1 is the first entry. So, H 1 times grad H 1 plus H 2 times grad H 2. So, this summation will turn out to be the matrix vector product from here. And then when you try to differentiate this once more to get the Hessian of the penalty function, then you will find this thing into grad H transpose, that is keeping this constant differentiating this, plus the second term sigma H I into del 2 H I by del x square, that is keeping this constant differentiating this. Okay. Now, what happens is that towards convergence in the later iterations, this part will be small, because H I will try to converge to 0, if your algorithm is working any good. Okay. And this is anyway second derivative. So, this product will turn out to be small, and this more costly term, computationally costly, okay, computationally inefficient calculation, this if you leave out, then you will be left with this. And this grad H is a matrix, grad H transpose its transpose. So, this matrix grad H transpose is termed as A, that is a rectangular matrix which is fat and short, okay, more columns, less rows, and this one is its transpose, this is a tall matrix. So, what happens? This entire product is a large matrix n by n, okay, because it is a second derivative with respect to x, which is n dimensional. However, this is the product of A transpose A, okay, and it cannot be a full rank matrix, because you have the m by n matrix which had at most rank m, and its transpose n by m matrix which also had the same rank. So, the product can have at most that same rank m, but the matrix is n by n which is large. So, this is certainly singular. Okay. So, this is the issue which says that Hessian is extremely ill conditioned. Why? Because the Hessian of this term, penalty term, is certainly singular, and when C is sufficiently large, then the Hessian of the Q function f plus C times penalty function, that will be Hessian of f plus C times Hessian of P, and this is certainly singular, and this is something. Say even if this is positive definite, its eigenvalues are 1, 2, 3, 7 kind of things. If this has 3 eigenvalues which are zeros and 7 eigenvalues which are 4, 5, 7, 8, and this C is 10,000, then that 4, 5, 7, 8 will become 40,000, 50,000, 60,000, 70,000. So, in terms of 40,000, 50,000, 60,000, 70,000 for huge eigenvalues, the other 3 eigenvalues which will be extremely small, and that leads to ill conditioning. So, in the solution process, whenever you encounter the linear equations, they will be extremely ill conditioned, and you will have difficulty in solving them. Okay. Tangent plane is this, keep that in mind, and then you will notice the identity of A. What is A? You will notice from there. So, in the case of using modified Newton's, for example, modified Newton's method, rather than Hessian of the objective function plus this, you can as well use identity plus this, because in place of Hessian of the objective function, whether some proper matrix is sitting or simply a dummy is sitting, it does not matter. So, that is one cost saving measure you can take, okay, but the ill conditioning will still remain. Okay. And in the solution process, you have to use some special measures by which you can avoid the trouble of ill conditioning, and you can increase your computational efficiency. The corresponding little exercise, the linear algebra exercise, is there in an old assignment, assignment 1. Okay. If you are using conjugate gradient method for your ordinary unconstrained optimization, then you can rest assured that a typical cycle of n iterations are not going to take place in a healthy manner. Okay. So, you may make a partial implementation of that there is only a few iterations when things take place properly, and beyond that you consider a restart. Okay. So, that is a typical conjugate gradient method that is applied for pure penalty methods. Now, in between I have started talking about the so called pure penalty methods. What is the matter here? Because penalty methods is a kind of easy quick fix solution for a constraint optimization. Okay. So, if you have forgotten all the constraint optimization methods, then conceptually you can say that for every constraint, if I put a huge penalty, or if I increase the penalty slowly over iterations, say equal to 1, 10, 100, 1000, 10,000 and so on, then I can get hold of some solution by the ordinary unconstrained methods. With that you can handle it, but if you remember your proper constraint optimization methods, then other methods are likely to be more efficient. Okay. So, that is why pure penalty method you can use, but they will be typically inefficient, or typically they will operate in an ill conditioned manner. However, even if you do not use penalty methods entirely, you use other sophisticated methods from one of the other three families of methods, still the concept of penalty is useful in two senses. One is that in very simple problems you can use a pure penalty method and get rid of the problem, have your solution in hand and proceed with your design. And even if your problem is complicated, it is not simple and you are using some other method, there also there are some little intractable issues that do not fit well within the framework of those other methods, and there those little issues, those little quirks, now and then you handle by using a little penalty term. Okay. The way we also used in this particular case by using this parabolic penalty function. Okay. So, this is what penalty methods are useful for. One, solving very simple problems quickly without much of a programming effort. Quickly means quickly so far as the programming effort is concerned. Your actual computational time will be perhaps more. If you do not want to take the trouble of a proper, nice, careful coding, or if you have forgotten many methods and you do not have the time to go through them again and you want the solution quickly, let the computer run overnight, does not matter, or 10 minutes, does not matter. So, then inefficient working, but your programming effort will be less, it will be easily handled. This is one thing, and the other is to give little supports to other families of methods. Okay. So, these are the things which you have to keep in mind in penalty methods, and in the next classes we will consider the other three families of methods: primal methods, dual methods and Lagrange methods. Okay.